So thanks to ISA for the invitation to be here. I'd like to share with you some updates on some work that I think exemplifies what ISA does with the U of I, but also what ISA has been doing by pulling together different kinds of stakeholders. And this is a project on liming. It's a project on pH, which is always this awkward aspect of fertility insofar as that there's lots of, I think, misunderstandings on what is buffer pH, what's reserve acidity. And my goal today is to walk through an example of the kind of research that we're doing at the U of I with ISA and with on-farm partnerships to try to both get good data, but also to demystify what actually happens when lime goes onto fields. So if I can accomplish one thing today, it's to make you not be afraid of the term buffer pH. If you don't even know what I'm talking about, then hopefully you'll understand what that term means. And then I'll end by priming you for what's coming down the road. And the short answer is that I don't have answers today on the specific lime recommendations, but they're coming. We're going slow and steady to get it right. So with that said, I'll get into this topic of liming. I'd like to begin with some acknowledgement of the supporters. So this work was curated by ISA, but there were contributions financially from this network that you see here. This is part of a larger program that our lab has on P and K. Liming is part of that. It's not like P and K in that you're not putting on a nutrient, but you're moving the master switch of pH, which impacts everything else, including plant root growth. So these different partners were put together by ISA. They pitched in some funds to fund this project that you will be hearing about. Alrighty, so with that, I want to begin by pointing out that the on-farm section was then additional funding where we leveraged the ISA stewarded investment, and then we said to other folks like Growmark, like iCorn, INSA, a new group that was founded at the U of I last year, and said, hey, ISA's put in this amount of money, can you match that? So we've been able to grow this investment, leveraging, to do an on-farm component. So we have now not just lab results, which are important, but they're not the only. How about this? We have to go beyond the lab for soil fertility, and we have an on-farm component. So the work, there we go. I'd like to begin with this potential myth, and it's a question mark. And I'm open to questions or to answers by the audience. Is it a myth that soil pH is sufficient to determine a lime application rate? So can you take a pH value from a soil test, which is done in water, you mix soil and water together, it gives you a number. Can that number tell you the other number of how many tons of lime per acre do you need to hit a target pH? I'm curious to hear any thoughts from the audience. I'm seeing heads nodding no. Does anyone care to elaborate on why that might be and steal my thunder? Yes, sir.
Clay colloids will have protons as well.
That's right. So to translate the excellent science, protons are H+, it's acidity. And so clays hold on to the driver of nature that causes pH to go down. And that's exactly right. So when we're shaking a soil sample with water to measure pH, what you get back on your lab test result, that's simply a snapshot of the partial acidity of the soil. And this is what we call reserve acidity. It's held in reserve. It's like your bank account. There's a withdrawal limit. You can only take out, I don't know, $500 per day for some banks, but you may have $10,000 in there. Same exact metaphor is that what you're taking out of the bank account, the withdrawal limit daily, that's your pH in water. But there's a lot of backup. Hopefully it's a big backup for the bank account. For soil pH, maybe hopefully it's not that bad. So to image this, it kind of looks like this, or someone thinks it looks like this, where you've got on the right-hand side what I've circled there in the green, that's what you're measuring as the protons, the H+, the acidity dissolved in water. That's what your soil pH is at any given moment. And that will fluctuate over time, even by hours sometimes. All the other stuff on the left-hand side is going to be the reserve acidity, the stuff that is bound to, as he said, the colloids, the clay particles that are very good at storing the H+, the protons. So this matters because if we're liming a soil, we are trying to neutralize both pools, both kinds of acidity, not just the pH driven by the water protons, but also what is held in reserve. So this is why pH in water is not really by itself sufficient to inform the liming rate. And I'll show you some data on what would happen. It's not a disaster, but you don't really get accurate use of lime, which means it might be over or under applied and thus lost profitability for different reasons. So then the whole point of a buffer pH test, and you will hear that word a lot, is it is a soil test that is measuring the pH when you account for the reserve acidity. It goes a step beyond that immediately dissolved in water pH. So the reason why we are doing this work is that most states across the Corn Belt, the soybean belt, have moved on for their lime recs to talk about buffer pH. It is a newer way of testing how much lime do I need. But the state agronomy handbook and state recommendations are still using an older way of doing this without buffer pH. So we get a simple question. How good are those recs? How well do they stand up compared to the quote-unquote more modern buffer pH tests? And if we're to make lime recommendations for Illinois croplands using buffer pH tests, which buffer pH is best? Because there's not any one such thing as a buffer pH test. It's a class of tests. All right, any questions so far after the deluge of soil chemistry? Alrighty, if not, then I will continue. Great. So I want to go back in time. I love looking at historical stuff. I'm a history dork when it comes to ag stuff. This is not a new idea. This has been known for a very long time. The Roman agronomist like Cato in AD 53 was talking about liming soils that are sour, acidic. This is well known to mankind. What is different here is in the last century, we have tried to be more precise on how much lime do we need. And I think this is well captured by the title of this book, by my predecessor from 1915, Cyril Hopkins. Dr. Hopkins was the first soil scientist for the state, and he talked about this concept of bread from stones. He had two kinds of stones in mind. One is rock phosphate, which is to provide phosphorus, but the other stone was limestone. And so it's a very nice title, Bread from Stones. He's talking about wheat production as a function of rock phosphate and limestone. But the idea was that we need to go beyond flat rates of limestone application and going into dosing it in a way that's profitable. Are we over-applying and thus wasting dollars, or are we under-applying and missing out on yield gain dollars? Wrong direction. And so if you crack open these writings by Hopkins over a century ago, he's got some pretty basic yield response trials. And so they were trying to calibrate liming rates based upon yield response. It's clever. It's very clever when you have no way of measuring pH. So think about that. Soil pH was not measurable until about the 1920s with accuracy and with low cost. The first ever measurement of soil pH, any guesses what year or what century it was? The first time that a human measured protons in the soil was, any takers? It's okay to be bold and throw out a crazy year. 1858. Very close. Excellent. So 1858, the British report the first measurement of soil pH. We knew that pH mattered for things like stomach acid, for the manufacture of steel and iron. So by the 1820s, pH was understood. It took a long time to measure. Now it takes us 30 seconds, and it costs basically just the labor of the student to do it. So 1858 was the first routine, or let's say reported measurement, but really the routine testing of soils for pH was not until about the 1920s. So this is penned in, I think, 1913? There's no real way to offer farmers or crop advisors a way of measuring soil pH. And now we know that, by the way, you can't even use soil pH to predict the lime rate. So pretty clever. When you don't have a tool, you have a workaround. That workaround was yield-based calibration of lime rates. So fast forward to about the 1980s, and since then, we've had this table, which is from Chapter 8 of the Illinois Agronomy Handbook. Chapter 8 is titled pH, P, and Other Nutrients. I think K is in there too. But it deals with the non-nitrogen inputs to soils. So this is the current state recommendations. There's been various iterations since the first edition in the 1950s. I forget which one we're on, but it's been basically unchanged for a while when it comes to this section that you're seeing here on Lyme. This table looks like the Rosetta Stone to me. There's a lot of different angles you have to match up, and you need a ruler to match them up. But the principle is pretty clever again. It's simple. The whole idea is that if you have one of 6 different kinds of soils, A through E, based upon organic matter and CEC, you find out where your soil type is, A through E, and then based upon the soil pH that you measure versus the target, you can kind of estimate the tons of limestone per acre. So it's using 2 easily measurable or even visible attributes of a soil type. CEC, which is part of routine lab tests, and that even itself can be estimated by the texture, how much clay there is. More sand, lower CEC, etc. So again, this is not unlike Hopkins in 1913, and I'm a fan of simple. I don't think we need to over-engineer everything. This works pretty well. But the question then is, should we, as a state, move on from this simple and usable approach, that's not going back, to the buffer pH? So reasons to go to buffer pH is everybody else is doing it. And my dad would say, well, if they jump off a bridge, would you do so too? So there's not a good reason to do it because all of our neighboring states are doing it, but it would raise an eyebrow that we're the last state to not be officially recommending Lyme rates on buffer pH. Second is that it might just be more quantitative. 5 soil types for the state. As a soil scientist, it's probably workable, but we have 57 major soil types. So there's reasons to go for a numerical approach, so measuring a buffer pH number, then a categorical, categorizing soil types into groups based on 5 different entities. And it comes back to this, is that we want to be measuring the pH in water in green, but also this other thing, this reserved acidity. And how you get that is by a buffer pH test. Now then this presents the question, which buffer pH test? If you didn't know, now you know that there is a thing called buffer pH, and also that there are 9 different types here, major types. Some of these are on the books, they're hardly used. Some of these are specific to one state because the professor there made it, and it's their baby, and you're gonna use it in Georgia, for example. And there's also not any harmonization of not just which test is used across states or regions, but also how you interpret those results. So it's the state problem. Every state does things differently. That's good, but this is an example of the not so good. So in our region, in general, we use the most variety of buffer pH tests, further complicating the issue. We also have pretty high soil diversity across the Corn Belt, so I think that this would make sense. Now, they all have the same goal. There's just different pathways, and some of these are more appropriate for different parts of the country. So on sandy soils, Adams-Evans might be better. In Georgia, the Melick buffer pH, not to be confused with the Melick p-test, is more appropriate. They were made for those soils. But still, we wanted to check out, could some of these work in Illinois systems? So 3 things to think about and 3 takeaways before I talk about what we found. The first thing is that buffer pH is not a single test. It is a category of tests. So that's important because different tests will give you a different number for the same soil and thus a different Lyme recommendation potentially. So always ask, what buffer test are we talking about? Second, that the Lyme rate is partly coming from your buffer pH, but you want to think about what your pH goal is. If you're trying to get up to 6.8 versus 6, the same test won't tell you how much Lyme unless you specify what the end goal is. So you, the human, must decide where are you going with the final pH target. And third is that the calibrations that we have made, as I'll show you, depend on what they're calibrated on. So ideally, the entire US bands together every 50 state, and we do a massive study with 3,000 soil types, and now we have a way of having a universal buffer pH test. That won't happen. It doesn't make sense either, I think, for good reasons. I bring this up because if you see Lyme Rex from, say, Kentucky, just be aware that even though they use the same buffer test as Illinois labs do, they're based on Kentucky soil type calibrations. So buffer, pH test type, your target pH, and then the region of calibration are all things to consider. So to boil this down as 3 takeaways, what buffer pH test is being used? Find that out. Second is use a regional calibration when possible. We don't have them yet for Illinois. You're about to see them for the first time. And third, what's your pH goal? And this is kind of arbitrary. Once you're above 5.5, you avoid aluminum toxicity to roots. Under 5.5, there's a real problem. 5.5 to 6, pretty good gains. Above 6.5, arguably not a huge deal. That depends on experience, on cultivar and hybrid, but in general, getting at least up to 6 is probably a safe bet. Depends on the price of lime. If you get a good deal, get up to 6.8 and coast downward for a few years. So what we did here is that we took soils across the state. We took 48 soils and then we thinned it down to 24 for what you're about to see. But there's a twice the size data set. And you might be thinking 24 seems pretty thin for the soil type diversity of the state. It is and it isn't when it comes to the reserve acidity question. So these soils definitely differ in organic matter content, CEC, but they encompass a range. And it's the range of properties that we're chasing, not all possible combinations of those properties. So we've got pH from about 3.8 to about 6.5. We didn't go above that because who's going to lime a 6.6 to 6.8? At least for our purposes, that's not of interest. We looked at CEC as a property, getting under 5 for CEC, so that's basically just sand up in Kankakee, up to about 30, so pretty good. And same thing for clay content all across the spectrum, and same for organic matter by about a 5x range, from almost none to 5% OM. So these are pretty representative in terms of the range of properties. Okay, so what we did in the lab to compress 2 years into 30 seconds is we take soils and we add lime in controlled conditions. I realize this is not the field, and that's why we have the field component. But this is how we get the best possible chemistry answer to the question of how much lime do you need to raise a soil pH to this target? And to take away the variability in weather, environment, applicator, this is the best possible way. So we do this over the course of 8 days with slaked lime. Slaked lime reacts much more quickly than calcium carbonate, so limestone, or than quicklime. And we do it over a range of rates that are equivalent to 0 to 8 tons of lime per acre. That's the equivalency on a CCE basis. Basically, it's done in 8 days. We keep them wet and warm. The reaction happens quickly. Again, the point is that this is highly controlled, so it's the highest confidence chemistry answer to how much lime do we need. So let's talk about these results. The first question that we oftentimes get is can I just put on a flat rate of lime? And I want to start here before we show you these results on calibrations of buffer pH. This is a fair question. Maybe there's an opportunity to spread lime. It came to you pretty cheap. The weather turned out to be in your favor. And the question that we get is, what's a safe blind rate? So blind meaning you don't know even what the water pH is. It's just the field and you have a chance to spread lime. You suspect it's under pH 7 and that's about it. And what we did is that we looked at if you want to stay between 6.5 and 7, those 2 horizontal red lines on that figure, if that's the sweet spot to get to, and we don't want to go above 7 and certainly not above 7.5 because things get very weird very quickly, what would happen if you applied lime from 0 to up to 10 tons per acre without knowing the pH beyond it's under pH 6.5? And what we find is that 1 ton per acre of lime gets you to pH 6.5 for half of these soils, which are a range from 3.9 to 6.5. If you were to put on 2.5 tons, then most of your soils hit pH 6.5, and by the way, most also get above 7 at that point. And if you go up to 3 tons per acre, all of your soils hit pH 6.5, and now nearly all of them are above pH 7. So this is just to illustrate that the flying blind approach can be dangerous because it's easy to overshoot pH 7, and once you're above pH 7.2 to 7.5 onwards, you get tie-up of phosphorus, of micronutrients like zinc, copper. It can be not exactly agronomically safe. So this is why the whole dosing matters. All right. So then the next question is, what if we just use water pH, soil pH on the test? There's no buffer pH here. And what you're seeing here is a graph of the soil pH on the x-axis, so from 3.9 to about 6.4. And then on the y-axis is the amount of lime that you would need to get to pH 6.5. So the R-square is the metric for this discussion. It's crude, but it gives you a rough sense. You want the R-square number to hit 1. So it's about 0.43, which is saying that you've got a pretty low ability to explain, to predict what your final pH is going to be. Meaning that this is better than flying blind. You get a really rough approximation of how much lime you might need based upon the pH. But why not use a buffer pH? Now, you might, if you've got a keen eye, you note that there's this outlier. So the soil that's pH 3.9 looks to be off that line. So if we drop that from the data set, and now we're talking soils that are in the range of, pH 4.8 to 6.4, which is arguably most soils. I have seen soils of pH 3.5 down south around Effingham. But for most intensive uses, this is not the case. So in this context now, the R-square goes up. So this is not terrible. In other words, if you have the option to spread lime in a way that makes sense, profitably speaking, the water pH might be reasonable, but it better be cheap lime because you're going to be more or less 60% there, accuracy. Okay, so to summarize this, soil pH in just water is a poor predictor, but it is a predictor versus flying blind. You're just throwing lime out there, good luck. Can we do better? We think so. And so this is the next part of the talk is let's talk about how to precise this beyond soil pH. So this is where the current state recommendations come in, and then the buffer pH comes in. Again, buffer pH accounts for more of that acidity than this approach that you're seeing. So the question is really simple. Are the current state agronomy handbook recommendations reasonable? Are they accurate? Can they beat out water pH? Can they even hold their own against buffer pH-based recommendations? So to break this down in a bit more detail, we've got the soil types A through E, 6 types of soils. No, my math is terrible, 5 types of soils. I'm a soil scientist for a reason, folks, not a mathematician. And so we can categorize these based upon texture and color, because color is a proxy for organic matter and the CEC very roughly. Long story short, we then looked at these. I'm going to get right through these assumptions. And we looked at the lime rate that we know that we need, which is the x-axis. So this is what we measure in the lab. This is what we know to be as true as possible. And then on the y-axis is based upon the agronomy handbook. And you can see that there's actually a pretty good R-squared compared to water pH, which was about 0.4. If we drop the outlier acidic soil, it went up to about 0.6. So the state agronomy handbook recs are doing a decent job, especially at the lower lime rates. The points are closer to that line. This is overall encouraging, right? But can we get that R-squared up higher to 0.8, to 0.9, to 0.95, almost to 1, which would be incredibly high accuracy? That's a good question. So I would say that under the lime rate of 1.2, these handbook recs are reasonably accurate. So more acidic soils are less accurately predictable for lime rate by handbook recs than less acidic soils, to put that differently. All right. We also looked at these based upon 2 ways of measuring the CEC. So the left-hand graph is on what we measure as CEC the best possible way. The right-hand side is what you get back from a commercial lab. It's a quick and dirty estimate. It gives you about these same numbers, so that's good news. So the takeaway is that these recs work pretty well without a buffer pH. They're pretty good. They certainly beat out the water pH. Good news. So next question is, how do buffer pH tests compare? So for this, we have 3 of the 9 buffer pH tests that we had looked at. The 1-to-1 line is comparing the known lime rec with the lime rec based upon the buffer pH test. And so a good buffer pH test for Illinois soil types would be exactly along that 1-to-1 line. So we've got 3 of these, and they're out of order, I apologize. Adams-Evans, modified Melick, and the Socorro/S&P that we grouped together for this purpose. So a few observations. Adams-Evan is way off that 1-to-1 line. So the points cluster well with a decent R squared, but they're going to be underestimating the lime rate. So Adams-Evans is not a tenable buffer pH test for lime racks in our state. They underestimate the lime rate by a factor of 2. You're half under. The modified Melic from Georgia and the Socorro S&P made here in the Midwest, these are pretty good. Our scores of 0.83, 0.86. Remember, the handbook was 0.76. Water pH was 0.6 at best. So we're nudging closer to more and more accurate tests. Leaves a lot to be desired, right? I'd like to see 0.95 to have full confidence, but if you know about soils, that's probably not going to happen for a wide array of soil types such as this. So the takeaway here is that the current widespread use by most commercial labs that service this state, they tend to use the Socorro and or the SMP. That's in fact adequate. They figured it out, of course, but that's a fine test. But what we've overlooked is that the modified Melic test made in Georgia works very well for this state, and it's a lot cheaper to run for commercial labs. So there might be cost savings on the soil buffer pH testing, and thus saving the advisor or the farmer on testing for lime rate. Okay, so I'm going to pause there. Any questions on the chemistry? Thank you for going along on that ride. We're going to now talk about field stuff, but before that, I see a question from Brandon.
Yeah, so rarely in Illinois, when I'm looking at soil tests, I rarely see a 7.0 or higher. Why is that? And so that's even if guys are religiously putting online, over time, needed or not. And then the other question is, I had a guy ask me about liming, we're spoon feeding a lot of our nutrients anymore. Would it be better to spoon feed this lime 1 ton per year on every acre, or put a large amount, maybe 3-4 ton at one time, so the benefit of both?
Great questions. First question is,
Could you recap that just a little bit for those online?
Yep. The first question, I believe, was why don't we see pH above 7 for most soils? If you dig down deep enough, they'll become pH 8.5 across the state. So we've got the luxury of very high carbonate-rich parent material loess. But you're right, for the surface depths, we don't really see above 7 anymore. If you look at old data pre-1950, before the use of Haber-Bosch nitrogen, soils following prairie were roughly around 6.8 to 7.4. But we've been adding so much N that it tends to nitrify. We produce acidity. We correct that with limestone. So I think it's simply we've decreased from N inputs, and we've not limed up beyond 7. That's a hypothesis. That's not a for sure answer. Second question was
So putting lime at 1 ton.
spoon feeding.
Yeah,
Okay.
like spoon feeding lime every year versus putting, 3 or 4 ton at one time.
Sure.
And then having that, do it.
Thank you. So for the audience online, the question is about why not spoon feed, or what if you were to split apply lime over many seasons versus putting it all up front as 4 tons versus 1 ton over 4 years? That's a great question. I don't have an answer for you. Some thoughts. I think the source of lime matters. If you're applying quick lime or slaked lime, that'll react immediately, in which case spoon feeding could work. If you're adding low grade, low CCE ag lime, that might take longer to release, and it does. This also interacts on soil pH. Lower pH soils will react more quickly. So there's this interesting tension, and I'm not really sure how that would go. So not a great answer for you. I would suspect that the economics of having to go out every time and spread it may offset any of the benefits. That would be my guess. Great project, though, to test. Thanks, Brandon. So speaking of field experiments, here's one that we did that we then took all this lab-based data and we said, okay, this is great for the lab. So far, we've now caught up to every single state, and we plan to publish these and update the handbook recs on buffer pH. But what happens in the field? So if you take the same soil and you add a lime rate that the test tells you, do you see the pH change? And then to Brendan's point, I think, how quickly do you see that change? So I'll focus on the yield data because the pH results are not in yet, but this addresses a separate question, the second question here, which is, do you see effects on yields in the next season? And there's concerns that if you add too much lime in 1 year, it'll maybe drag yield the following year. There's lots of mechanisms here. There could be P tie-up, there could just be too much calcium carbonate for the roots, etc. But it could also be argued the converse, that you might see a bump within the next year. So we focused on the fields that are coming out of corn into soybean. These are all fall-applied fields under pH 5.5, so they're pretty acidic. We did this at scale in 6 different sites across 10 sites across 6 counties, largely central south. This is thanks to Growmark, who helped us find the farmers. And then we applied lime at just 4 rates, 0, 1, 2, 3. Keep it simple. What did we see? We think that 3 tons is safe if you're under pH 5.5. And we did this at each replicate of the 3 reps per lime rate was 0.74 acres. So these are not small plots on a campus station. These are at scale on a commercial field. So I'm going to focus on 4 of these sites that I'd characterize as high and low yielding environments. These are the soybean yields in the following season from the previous fall's liming event. So you've got the lime rate here from white 0 to darker shade up to 3. You've got the 4 sites, and as you can see, 3 sites gave great soybean yields, some cracking 100 bushels and some being barely above 35 bushels. And we're curious to know this because you might hypothesize, you might expect that maybe lime matters more for low yielding conditions and higher or vice versa. So this is the data. To walk you through, we see some sites where there's basically no yield difference, even as an average value. Without even applying stats, we can say the lime rate had no effect, fall applied out of corn, on soybean yields the following year, whether these soybeans are making 85 plus or 25 to 30 bushel. Same soil types, by the way. And then we've got some sites where we see noise, but then statistically, these are not significant, meaning that there's less than 5% chance that this is a real difference when you see one bar higher, lower than the other bar. So it raises an eyebrow. Maybe if we had more replication, we would detect something, but really doesn't matter. So that's the other point, is that there's no definitive increase, but also no definitive decrease in soybean yields, and these are high yields, following fall-applied lime, up to 3 tons per acre. So that's the takeaway. There's no clear yield effect within that following season for soybeans. This is good and bad, right? It's safe to apply in these very acidic soils, up to 3 tons per acre, but don't expect a big boost in yields, at least for this season. It was also a crazy season down south, very wet, and then the spigot turned off, so that might matter for the plant response, like Dr. Van can tell you. Van, excuse me. Alrighty, so we can look at this data a little bit differently as a relative change. So here we've got the change in yield, because these yields go from 35 to 95 bushel per acre average. We can normalize as what's the percent or what's the bushel per acre difference. And there's not really anything here that pops out statistically, it's all noise. And same goes for the percent change in yield. These graphs look almost identical, further supporting that there's not much here. So the takeaway then is that across these fields that differ by 3.3 in yield, from 30 to 95 bushel field average for soybean, there's a consistent lack of a yield response. And you could say that it's within plus or minus 5%, but again, that's not meaningful statistically. So again, takeaway to hit home is that soybeans are safe following fall lime in sufficiently acidic soils, up to 3 tons per acre. All right, to summarize all this, liming is key to maintain soil productivity. This manifests at longer time scales. We don't see a yield response like we do for N or even P and K. It's a trickier, not a nutrient, but aspect of fertility to manage. This has been known about for over centuries. Only in the past half century do we have the tools now to precise how much. And so this is now today informed, we think, in the best way possible by using buffer pH. So what we've been doing with this project is confirming that pH just in water, as we opened on that potential myth, it's decent, beats flying blind, but we can do better. And that's where the buffer pH tests come into hand, but also the current agronomy handbook rates. They're decent enough if you don't have a buffer pH test. And for our region, it turns out we've confirmed that the S&P in Socorro works, like what Iowa uses, but we've also identified a new and a cheaper test, the Melick buffer test, for lower cost buffer pH testing in the Slime Rex. The field trials point out that there's no yield response of soybean following fall applied lime from 1 to 3 tons per acre. Good and bad, depends on how you cut that. It's neutral. So what's next? Well, we're continuing on this project, which is in collaboration with a bunch of groups, including Growmark and USDA as well. They're trying to breed soybeans in alfalfa for low pH, so we're layering on these lime rates with them. We want to understand in the next 2 seasons of these on-farm trials the economic returns. So what pH does it make sense to lime up to and to hold that economically speaking? Just like P and K, I think we have to shift from yield response to net dollar per acre response. Lime is no different. So these will continue, and the final aspect is soil health. There's lots of good evidence that acidity is a real problem for soil health. And so what we don't know is how that might matter. So one reason why we know that liming improves soil production in the long term is that it's not just the liberation of fixed phosphorus, it's also probably due to increasing or fermenting more active microbes. So we're hoping to understand, is there any water held by that theory when it comes to liming soils in this part of the world? Alrighty, well that's all that I have. I used up a bit of extra time, but it's still ending early, I think. With that, happy to take any questions. Thanks for your time.
In the middle?
I know Brandon has some questions. Oh, you already asked? Okay. Right here.
Do you agree or disagree on the ROI or profitability of variable rate lime versus P and K?
When you say versus, you mean if you had to pick one to VRT? Well, that's a good one. You'd have to balance the prices of PK versus lime. You got me there. I would say it depends on your time scale, right? So I think in the long term, lime is going to be as important as P and K for investing in VRT. But in the short term, if you had to pick one, you have a 2-year lease, I'd just go for the P and K, in my opinion.
Behind you. Oh, go ahead.
Yeah, quality of lime, you talked about different lime throughout the state. I heard some mag problems in some of the lime that we're getting from some of our quarries. Can you talk on lime quality and where?
Thanks, Brandon. Yeah, so broadly speaking, there tends to be 2 major types of lime. There's calcitic, which is more calcium-based. CaCO3 is the formula for the nerds in the crowd like me. And then there's dolomitic lime, like the Dolomites in Italy. Those are magnesium-rich limestone, where you've got magnesium and not calcium that's pairing up with the carbonate. And so there's a lot of thought out there that if you've got high mag soils, like the flat and black, you don't want the dolomitic lime. We got plenty of mag here. You want the calcitic lime, and vice versa down south. You want to swap the sources. So the quarries up here are dolomitic quarries, and vice versa down south, typically, from what I've understood. I think it matters more if you're thinking about your mag from a CEC perspective, percent of CEC that has X amount of K, or X percent of K, X percent of mag. And if you're trying to manage nutrients on a percent of CEC that's calcium versus mag, it might be good to try to source the calcitic, so the calcium rich, over the dolomitic, the Mg rich. That said, the Ohio State did some work on this back in 2018 through 2022. And they tried to test this idea that is related on whether the ratio of cal to mag of your CEC matters. You know, tight soils that can be loosened by more calcium than mag. And they found no evidence that it mattered for yields or for soil quality, so aggregation and biology. Now that was in the context of Ohio systems, but just putting it out there, yeah. Sure.
Question, and you may have had the answer in what you just explained. This is the farmer simple version. In soils that have low pH and are showing low calcium, with the addition of, and limited tillage, with the addition of pelletized lime in a strip ahead of corn, 200-300 pounds, would that provide any benefit for that calcium number?
Relative to just non-pelleted, like normal ag lime, you're saying? No.
Here, I'm doing broadcast application of lime over the top, but there's just really not, in my system, not a great way to work that in. So adding a couple 100 pounds of pelletized lime, 6 inches in a strip below, would that help?
Great question, Jeff. These are really hard. You've all prepared to stump me. Short answer is here's why I could help, here's why I couldn't help, right? So I don't have a firm outcome. It could be positive because as you pointed out correctly, how do you place lime when you're not incorporating by tillage? One is the source. Faster sources in terms of dissolution are better, and the calcium carbonate works its way down. It's maybe good to pause here. Limestone works in two ways. The calcium removes that reserve acidity off the clays and puts it into solution, and then the carbonate neutralizes it. The calcium also pops off the Al because the aluminum generates more acidity. So limestone is a double punch. You want the calcium or the mag to displace and then the carbonate to neutralize and the rainfall to drag that all down, drag the Al down. Given that, there's evidence from Brazil where they do no-till that if you just surface apply lime and if there's enough rainfall, it will do its job. It just takes longer to work its way down there. So if you're in sandier soil types, broadcasting enough and waiting enough should work. I know that's super qualitative. So the economics might be worthwhile, like maybe the yield response that would manifest sooner to placing it with a quicker release form could be more profitable than applying on the surface and waiting for the rain to do its job. I think in higher clay soils, that's going to be too dangerous, so I would agree with placing it. The risk of placing it would be that you might have this hot spot of very high pH that could tie up nutrients and backfire and even cause plant roots to not get what they need. So I couldn't tell you with confidence which one's going to play out. I suspect you know the answer, though. Sure.
Do you have a question? In the middle?
I did, but it was answered in the.
Oh,
okay.
good. Good job.
Thanks.
Anything else? All right. Andrew, good to see you again. Thank you very
Likewise.
much.
Thanks very much.